Today I would like to do some prototyping and build some new systems that I would like to have in my game. As always, you can access the current development version as seen on the stream by following the link in the top left. And I would like to first show the new stuff that I have implemented. And to do that, I will need to I'm going to actually access the deployed version and not the current version. Let's see. Let me get the link. It's basically deployed on GitHub pages, and the link is this, and the working build is hosted there. So I made some trunks, as you can see. I made some shadows for the characters. I made this dust particle effect that appears when you place a character. I've also added some pollen that comes from the trees, and you can probably see it if you watch on the high enough resolution. Basically, some of the trees produce pollen, which I think looks great. And then I have also changed the title screen by adding some trees and generating the terrain in a way to kind of focus the scene on the game title. And I've also updated the credit screen, and now it works well with the depth buffer. And that's another thing, the depth buffer has been fixed basically by aligning the anchors of the sprites, and basically the Z buffer index is based on the Y coordinate, because it's kind of orthogonal, the isometric view viewed from the front, so we don't have any perspective. We're looking upwards with the camera, so it works perfectly fine, and it's a cheap way of doing it. And then I also added another enemy type, which is the bee. And these are their attack animations and death animations, which kind of makes the initial look more or less complete. Let's see the OpenToons project. I also cleaned up some of the older sprites and made everything kind of a bit tidier. And this is the dust that I have now currently, and it's also interpolated using AI with some cleanup. I think it looks fairly nice. And then another thing is the bee, of course. And these are the animations. And this time I managed to make the acceleration kind of work, because I was not even thinking about it when I was animating the first character, and it doesn't require too much time to go and fix it, but it's a task for later. It's a quality of life kind of thing. So that's fine. The shadow is pretty trivial, just a couple of frames, and in the end it looks solid, I would say. Okay, now on to more interesting things. The main thing I was working over the course of the last couple of days, it was the map. And the map, let me see. The map is, I basically made different attempts because let me make the classic old paint slideshow. Let's see. Let me get my pen. Okay, so this system is kind of important for the gameplay, the way I kind of envision it at the moment. And basically, we have two main game modes, right? The first game mode is what you are doing when you're not actively fighting. And then on the screen, you have some battlefield slots where you can put things. And then you also have your inventory slots where you can put things as well. And currently those things are only characters. And if you want to keep whatever you had in this part of the terrain, then you need to put the stuff in the inventory. And thus, when you proceed onto the next level, you take these things with you. Now, if you leave something on the battlefield while you are moving on to another level, you lose stuff. This stuff is gone. And so basically the two game modes emerge from this because every time you start a level, let me see if I can, yes, no. Okay, the deletion does not work as I wanted, but it's fine. So basically, when you start in the beginning, the level that appears, like all levels, use the abstraction of stage, and then the level abstraction is inheriting basic stage properties. And then the things such as the menu settings and the credit screen, those things come from the stage. And then there is this level abstraction that takes in some parts of the stage logic, adds a whole bunch of logic to manage the enemy waves, to manage the timers, the behaviors, the titles, the pause functionality. And those things currently are implemented in two different types of levels. The grasslands level and the home level. The home level is where you start the game. And since this both classes are levels, they both have a timer. And the timer per level for each of the levels can be a 0. The value of the seconds can be 0 or anything else positive. And if the default value is set to something higher than 0, then the countdown starts and appears in the top of the screen. And it also means that upon the construction of this particular level, the enemy waves begin to emerge and they move forwards. And if the victory conditions are met, then the timer, the amount of seconds, becomes 0. It is still a level. It obeys all of the logics of that are described in the level abstraction, but then you don't have the enemies. They are all dead. But you still have access to your inventory. You don't have the timer, and you can still place things in the level. And the reason it works like this is because I kind of want to build up on this idea and make sure that these two different states, where the amount of seconds is 0 and it's a passive environment, and a state where the amount of seconds is a positive number and it's a hostile state, are both representing two different game loops, and you do different things in those different game loops. The obvious thing, when you have enemies, you fight and you apply strategies and you apply the stuff that you have in the inventory, and also upgrades that are more general and apply, like more meta, and apply to the whole gameplay experience. And when you're in a passive state of the level, that's when you can do more interesting things. You can, like the most obvious thing, you can plan what goes into your inventory and what doesn't. After you purchase, after you get select the drops that come up when you win, if you don't have enough space in the inventory, the drops will be placed on one of the battlefield slots. And so then you can take something out, put it in the battlefield, and take something else. And that's the core of the strategy aspect of how you are preparing for the next level. Obviously, right now, there is no context. We don't know what's coming next. And we can only go to the right. And that's something that I want to change. Because the part, to me, it occurs that the part that represents strategy is where the meat of the the meat of the game happens. And thus we need to make this system interesting. Now, to make the system interesting, we have to have some kind of context. The context, the way I envision it now, comes from the global game map, right? So we have to have some sort of representation of the world, some kind of a map. And now we need to also know where exactly on the map of the game we are. And it would be very good to have a sort of upgrade that gives you the ability to see the map. That is, in the beginning, mostly covered with the fog of war. So you see a little small piece. And I also want the map to be completely procedural because of the roguelike nature of the game. We want the map to be completely different every time we create a new game. And I also want it to be deterministic and based on the seed. So then we need a system that generates the map, and we need some certain number of other systems, because it's not just random curves and splines that are getting generated. We need to have some sort of a structure, because I want the game to have a slight storytelling aspect to it, right? So in order to achieve that, I want to have, let me clean up the screen so I can kind of narrate my ideas visually. And hopefully it will make it more clear to me as well what it is that I'm after. So let's say we have the final map and it looks something like this. Nice cartoonish doodle style map. And then we obviously have some roads, right? That are different every time. Now, another thing that we would need is points of interest. The obvious type of a point of interest is the boss battles, right? Because boss battles, they yield something of importance to you as a player. And let's say we have some places with boss battles. Then we need the end game zone, right? So some of the roads would take you to an end game zone. Let's say this is green. This is where you finish the game. Then we need a starting zone. This is start. The green is end. The red is bosses. And we also need to have like hidden treasures, things that are nice to discover. And let's say we use blue for that. So behind every boss, there is a point of interest. And point of interests are also scattered across the map. Okay, so what do we need in order to make this system? And we want everything to be procedural. So everything has to not just be placed randomly. It has to obey some logic that ends up with a setup that makes sense to the player and makes the game fun. How do we achieve this? First of all, one thing that we could do, let's think procedurally. The first thing that I suspect we would need is different biomes. Each of the biomes will have a boss, will have a theme, and will have a point of interest that makes sense for that particular theme. How do we describe biomes? The way to describe them that comes to mind at first is using the Voronoi method. And basically what Voronoi method is, you pick some, like if I am to represent it visually, you pick some random dots within the given range. Then you start growing circles out of those dots. Like so. And the circles expand. Like this. You end up, when they are expanding, they are inevitably colliding with other circles that are also expanding. And you end up like if you've seen bubbles, you know, like soap bubbles stuck together, they form edges. And like sort of like the walls separators. And that is what is happening here as well. So it ends up being something, and I am drawing it very roughly. Something like like this, which is exactly what we are after here. We want zones. And then each of the regions can have a color. So let's say we have a red biome, and the colors we can assign randomly. So we place green color here, maybe blue across this tiles, light green on this tile, and then pink on this. So we end up with this kind of a map of biomes. Oops. Now, this thing is saved into a data structure. It can be even saved into a plain texture that we can, basically we just need some sort of data structure that we can query based on the position, on a coordinate. So let's say I want to query this position, and then it tells me, oh, you are in the red biome. I query this position, it tells, oh, you're hitting the green pixel, or the green biome, the green cluster. And this way, this thing will allow to set up some data for the procedural generation. So that's one thing. Then we kind of want the roads, right? And there are different ways of implementing roads, and I spent a few years working on a solution that would do that. And this is the Twitter where I was posting the updates for the road generator. And the method I was using at the time was the Parrish-Muller's paper, which is kind of like an L system that is growing procedurally and allowing for very complex, well, not very, but semi-complex road networks. And then I was building up on that paper, and then I went into a completely different direction to allow for many more features. But that's a different story. Another way of making procedural roads is using something like an A-star algorithm. It is a path-finding algorithm that, given 2 points, produces, and the grid, produces the shortest path based, the shortest path that is taken with the least cost of traversing the landscape. Now, the landscape in our case is 2-dimensional. And so one of the things that I did is I wanted to go with rectangles and not with just squares. And squares is basically a matrix, a grid. And then you end up having this sort of paths. And I did not like this look very much, so I decided to go with rectangles. And by describing a certain amount of points, and then filling this area with more points, making sure they don't come outside, because we want kind of the map, the traversable map, to be nice. We want it to be elliptical of sort. And then those things become interconnected like this. So we create essentially a two-dimensional mesh with vertices. And then we can select pairs of points, right? So the thing that we want to do is we want to select, okay, take this point and find a shortest connection, like so. But this is not enough, because we don't want our shortest connections to be composed out of straight lines, right? We want some organic feel to it. So each of the points will get a different cost. And cost in this sense is basically how difficult is it to navigate this particular part of the landscape. So for example, from red to green, let's say we have something like this. And if we say, okay, go from this point to this point, then, or maybe to this point, let's say this, let's say this point, right? And then when we are walking, we want to kind of avoid the red dots because they're very costly. It might be just like plain ocean, right? So we kind of go around them and we arrive here. Or if we are starting from this place, then we see, okay, we have 3 dots. The easiest to go through is this. So we go here, here, and then here, here, and here. So this is the meat of the A-star algorithm, basically, in a very simple nutshell. And to kind of make it work, the first thing that is needed is the algorithm that would allow for triangulation or for creating the landscape. Then after we have the landscape, so I am leaning to using Delanoator, which is basically an algorithm that allows us to remesh the given polygon and fill it with triangles, kind of. And then the triangles are composed out of edges, and each edge knows which point it is connected to. So this edge has this point in this edge has this point in the beginning and this point in the end. And this edge connected to this edge via this edge connected to this edge via this point. And so it is very useful because it allows for quick mapping of the mesh to a graph structure. And with a graph data structure, we can perform interesting things. We can do traversals of various kinds. And then the next thing is using A-star pathfinding algorithm and supplying it to nodes, which are the points in the terrain. And then this thing spits out an array of nodes. Each node has, in our case, a coordinate, XY coordinates, and it might have some metadata, right? And then this allows us to connect 2 points on the grid. But what we want is to have random pairs of points connected like so. And thus forming a certain landscape, road network, which is what I'm after. Now, when we have this point, the next thing that is going to happen so this is delaminator, graph, and a star. Now, what this is going to give us is a bunch of points, a bunch of paths that are connecting those points, and we end up having a bunch of splines, right? A bunch of polylines. The next thing we want to do is to smooth the polylines. So we can apply the Chaikin method, the Chaikin algorithm, to kind of make the sharp corners of the polylines smooth. So we want to have this because it gives it a more organic feel. Now that we have done this, next thing we need to do is resample these curves with a certain amount of dots. Each of the dots will be a separate level where you can battle or where you can put your base in, essentially. Now, hello. Now, after we get the Chaikin method to work and smooth out, and then we do the resampling. So we got the Chaikin algorithm, and then we do the resampling. After we do that, we get a bunch of different points. So we have these points, let's say they are resampled. And then there is another curve that is intersecting or is very close, right? Or does this, for example. And then we resample that curve as well. Like so. And we want the resampling to be uniform, obviously, for beauty reasons. It would look good on the map. Now, what we end up is with a bunch of dots, and they're not connected. So the next thing we need to do is to determine where the intersections are, right? So this is an intersection. And then we need to say, okay, in this point cloud, we want to make sure that this is an intersection. This is a separate road. This is a separate road. And so on and so forth. And then after we have that, we are able to convert this new set of points into the final graph that will be used for the actual traveling between the levels. And it will also help us knowing in which particular point on the map we are. It will help us knowing where the signs should be placed. So this sign could be placing up. For example, if we are, let's say, in this area, we can go up or we can go down. So that gives us context. And that allows us to strategize. It allows us to navigate the map. And it allows us to strategically decide which bosses we want to go to and which interest points we would like to get. That is if we know, of course, and the map is a bit explored and we have removed parts of the fog of war. It also will allow us to make educated decisions about which landscapes we want to perform on, because the biomes will affect the landscape, and the landscape can affect the gameplay, because some of the characters could be good on one landscape and perform inefficiently in other types of landscapes. Or the biomes, for example, if it's cold, some characters could just die upon being placed on the field because they don't have enough, they don't have sufficient cold protection. So this allows for a lot of variation within the game, and allows to make emergent gameplay. So this is great. Now, at this point, we will have the map. We will have a way to trace this graph. We want a new graph made out of this thing. And we can traverse this graph using A star. So after we go through these phases, we need to convert the point cloud into another graph that will be used and that will be cached and used for the game. Now the tricky bit is when we are trying to convert, we have this point cloud, and as we see here, the context that we have visually does not mean that we have the context in code. And basically we need to decide which point is connected to which, right? Because we need to make this thing into a graph now. And to decide which point is connected to which, we can't just sample in each direction to see who is the closest, because we could have situations like this. We could have situations like this where 2 points are close, but they're on different lanes. Now, in order to fix that issue, we need to use the data structure that we have here in this step when we have our resampled road, and it is a set of different splines. It's not just orphaned point cloud, orphaned points. Now, we need for each point to go and perform a hit test against the splines to determine which spline this thing is connected to. And then when we determine that, we can determine the interval of the point on the spline, because the spline itself, it can be a single spline, but the road can be like this, right? And then it means that if the dots are here, like so, it means that the closest point on each of the spline would be this. But we need this. We can't have this connection. There is no connection here. So in order to do that, we perform a hit test against the spline, the resampled spline, which are separate roads. And then we kind of ask, hey, what's your interval? So for this thing, the interval would be 0. For this thing, the interval would be 1. For this, 0.98, etc. So this way we know which point comes after which. And that way we can connect the graphs. I'm sure there is a couple of details missing in this thought process. But mostly it kind of looks fine to me. And the thing that I have implemented over the course of the last couple of days was this part essentially, which I'm going to demonstrate. So let's see. Let's access the local build. So this is what we have currently. And let's see. First thing that is being used, maybe I can, let's see, maybe I can do this and turn off the rendering of all the other crap. And then I can, let's see, turn off this. So we get this grid. So the first thing is I describe a rectangle with 4 points positioned in 2 dimensions. And then after this has been described, I apply the Chaikin smooth on this, like the red line. So it kind of becomes smooth and represents like a globe. And then after that, this thing is being fed into a delanuator. Now, a delanuator is a very interesting piece of software, and the implementation I'm using in this build is implemented by one of my closest friends, who happened to write it in JavaScript, and it was in the scope of my other project, which I showcased earlier about the generation of roads and the geometry around that. It never got to the point. I never got to the point of using it in that project, but this seems like a good application, and it's a very interesting piece of software. It's also, the implementation itself is efficient as well, and it basically it generates lists of triangles and edges, and each of the vertices, like, and the code structure resembles C code, and resembles like pointer-like access to vertices, and storing things in a flat arrays, much like you would do it in C, which kind of does not really use references and closures to save things. It's an interesting implementation, and I will also share the links to that implementation separately. I think it's a very useful piece of code. And then when the delanuation is applied, we give it a point cloud scale, which allows us to have different density of points within the boundaries. And of course, the interesting thing is that we can draw custom edges and loops within this thing, thus altering the traversable landscape or the shape of it, which is a very neat thing, and it can be recalculated in runtime as well. But I don't know if this thing is kind of useful for now, but it might very well be, and it's better than to just pre-generating the field, because then if I want to make adjustments, it would be much difficult. It's easier to have it done in runtime during the development phase. Now, after that, we generate the thing. We generate the mesh. And then the mesh is being converted to a graph. And for the graphing purposes, I'm using the ngraph.path library, ngraph.graph library. It's an npm package. And for the A star algorithm implementation, since I am not very keen on learning how to implement it and write it myself, just takes too much time. I'm using the ngraph.path library for that. So then the whole prototyping phase is kind of painless, mostly. And then basically I convert the data structure that comes from the delaminator into the interconnected graph. And after that, I run the A star algorithm from 15, for 15 different pairs, and each start and end is picked randomly currently. It could be based on a heat map, like a Voronoi heat map or something, which is probably what we will end up doing. And then the splines are resampled. I think. Let's see. So we do this. We can draw the mesh. Let's see. So this is the mesh, and then we can render separate paths like so, and they are not visible because we have too much crap going on. Let's see, we don't want the points. Let's see, what else are we rendering? This. So this is the result of the A star running across the graph, the mesh. And at this point we are here. Then I use Chaikin method and resampling here to make them nicer. And so we get a bunch of dots. Maybe I shouldn't use as many for illustration purposes. If I do this, yeah. So now these things are kind of becoming smoother, and they're being resampled. Now the next step is determining. Let me maybe do this. Let's see. The next step is, because some of the paths, they kind of go over each other, and we don't want that, right? Because if it gets to a point where we have, like, for example, one path following exactly the other path, then we kind of want to merge those things. So the next thing that happens is the merge. And here we can see the merged version with green dots. And if I remove the gray stuff, like so, and maybe add some width to the dots. So this is kind of like the merged layout. Each of the dots is a level. Now, the thing that should be done next is feeding this thing into a function that would compose a graph out of it, so that we can, let's see. So that we can build connections that kind of make sense, like this, like this, like this, and so on. And then we would get a graph that we could use A star against, that could help us with a feature like fast travel, right? Because then we can say, okay, so in this level, maybe use the brush. So in this level, we got access to a possibility to make a base, So we get like an upgrade that looks like a signpost or something. We place it here. And so this level becomes safe. We kind of make it very safe. And we continue with our journey, right? We started here, made a base here, and then we continue. And then if we want to come back here, we can open the map, click on the sign, and then we see the map, and just like in older RPGs, your troops start traveling. And there could be occasional, like when they reach certain nodes that are marked as like too hostile, they will have this like fast travel thingy interrupted and engage in a battle, which could also be like altered by like upgrades that you purchase, like traveling immunity of some sort. And then the fast travel is happening by doing some path tracing, because the point of interest, like or the hub, your sign could be here, and we could be way over here. Now, since we don't want to manually go through every level to get to where we were, we want the fast travel functionality, and for that we would need to find the best path to get here. And that's another thing. Since this is a system, like a mechanical part of the game, different implementations could be used here, or different cost functions could be used. So we can say, for example, if you're in the beginning, your fast traveling sucks, and it goes and takes on the hardest route you can get, probably, which results in more incidents on the road, so you will have to engage in more battles. And then when you get an upgrade, we use a different cost function that maps that plots a better route. So that could be a part of the gameplay, which is an interesting idea to toy with. And yeah, so that is basically the plan. And let's see. I hope this kind of more less hands-on version of the game dev diary was kind of interesting. Well, there is not a lot of me staring in the screen and trying to solve a problem, but rather thinking about the higher level features. And I hope by next time I get some answers and see what works and what doesn't work. And we will try to make a map out of this. I think it will be fun. Thank you guys for watching, and thank you to everyone who is watching on YouTube. I will see you folks next time.